Hey everybody, and welcome back to Linear Algebra Online. So the plan for this video is just review a few kind of important things from this really important chapter on eigenvalues and eigenvectors. So let's just get into it. So this first kind of slide is just a bunch of kind of key facts, I guess, kind of related, but also kind of unrelated, related to eigenvectors and eigenvalues. So one thing I feel like I haven't really ever written down or specified is this first point. So can we justify mathematically why if x is an eigenvector for A, then so is any non-zero multiple of it, okay? And so if we have like an eigenvector eigenvalue set up, right, like this, right, then it's really easy to just multiply both sides by like a constant. And the nice thing about constants with linear algebra, right, is that they can pass through the, they commute basically, right, with the matrices. Now this doesn't always happen with the matrix, but C is like a constant here, so it can do that. So I could also write this as, A Cx equals lambda Cx, right? And so that does it, right? So, this is any scalar. So if x is an eigenvector for A, right, then so is any non-zero multiple of it, right? So we don't want to let 0 be one of these. So like here, I guess I'll just say C can't be 0. There we go. Whoops, sorry. C can't be 0, partially because of definition, but also what I kind of want to talk about here. So if it is the definition of an eigenvector that it can't be 0, but there is a little bit more I could even say about it. So if you let x be an eigenvector, right? So if you have A times a 0 vector, I mean, it does equal lambda times 0 vector. It works, right? But there's a bunch of issues here, actually, and some of them are kind of deep. But one thing I just want you to see is that this would imply that there exists infinitely many lambdas, right? Because any number you want to put in here now makes this thing true, right? And that is going to be a problem, and it's not something you really see why it's a problem until you get to learning about stuff called spectral decomposition, and which I think Endgame made some people hear that term way ahead of time. But there's actually things down the road in linear algebra where having infinitely many eigenvalues would throw off some important results. So also, it's just one of these things, if, I'll try and draw this, if this is your normal xy coordinate system, in linear algebra what we're doing is you might keep this here, but then, the y-axis moves here. But all the grid lines, if I had this one, that one might move to here or something like that. There needs to be a nice spacing issue, and one of the things that needs to happen is that the 0 vector stays put. So the 0 vector kind of trivially always works as an eigenvector, but the eigenvalues for it make no sense. So it's kind of not an answer, but just kind of know that it's going to mess up a bunch of results down the road, and it's trivial. It doesn't help us in any way. It's nothing important that the 0 vector is staying put. That's the whole idea of linear algebra, is that we transform space, but this vector stays put, right? If that vector moves, then it's not linear, actually. So there's something weird going on if that moves. This last part, super important. If you take away one thing from this whole unit, it's that eigenvectors are the vectors that stay in their same span after the transformation, right? So you might have, something with, I don't know, what's an easy example here, like a projection, right? Maybe you're projecting everything down to the x-axis here. Then, these vectors that are on the x-axis, like these ones, right? These kind of things would stay in their span after that projection. So that's what eigenvectors are. And the value, right, is just the length of the scale factor, because they can stay in their span, but they could double or half in size or whatever. And that's all an eigenvalue is. So I do have to, I feel like I'm obliged to do one of these. So I think it's good to just see one more example by hand, finding eigenvalues and eigenvectors. If you feel like you're really good with this, I would still watch it just on like double speed or something like that. But let's get into it. So first step is to always just take the determinant of a minus lambda I, okay? And then we're going to set it equals 0, right? So we're going to solve that polynomial that pops up, okay? So in this case, we're finding the determinant of minus 3 minus lambda. Well, I'm just going to pause the video. So we need to find the determinant of this. And we set that equal to 0, right? And, you know, this one is one where I don't think there's any row that's like particularly easy to expand along. I think I'll expand along the middle just because some of the numbers are a little smaller than other rows, right? Like, I don't know if I'd want to expand along this with the 20 and the 10, but I mean, it's still going to pop up somewhere. So if I do this, basically what I am going to do is, if I expand along the middle column, it'll look like this. Okay, I'm barely squeezed in. You can see my beautiful spacing with my writing. And these are separate terms, right? Minus 3 minus lambda, then minus 3. So it's the negative expansion along that one, right? And then plus on that one, and then negative on that one. Then you got to crank through all that. So I'm going to pause again and do out the algebra. You get that. And then I'm going to just combine like terms. And I would get minus lambda cubed plus 4 lambda squared plus 3 lambda minus 18. And that all is set equals 0. So I might also multiply by -1. So really the polynomial, the characteristic polynomial would be lambda cubed minus 4 lambda squared minus 3 lambda minus 18. And it's one of these where you basically have to do, you might try factor by grouping, but you might also, you'll see that that won't really work because the ratio of these terms kind of doesn't make sense, right? 1 to 4 is not going to help you with 3 to 8. So there's no like common factor that you can take out and get another factor there. So I would basically just do rational root theorem. And by that, again, I just mean this. I usually use P and Q when I teach this in algebra, but it's like the possible rational roots would come from factors of the last term, 18. So 1, 2, 3, 6, where was I? 3, 6, 9, and 18. And then over factors of the first term, which is really just 1. And so then you go and typically I tell my algebra students just use a calculator, get one root, and then start doing your division. So in this case, you can see that, like, for example, 3 is a root. So I would do synthetic division with 3. So -4, -3, 18. I'd bring that down. This would be -1, -3, 6, oops, -6, -18, 0. And so then we're reduced the cubic down to this quadratic. And actually, I'm going to hit factors, nice. So we would get lambda minus 3, lambda plus 2 equals 0. So we've got eigenvalues now. So we have 3 as 1. And then from this, we can see that lambda equals 3 again, and -2. So we've got 3 with algebraic multiplicity 2, and we've got -2 with algebraic multiplicity 1. That is the eigenvalue part, right? And then you have to go through and do the eigenvector part. So this is where you can actually, I'm okay with using your calculator. So we're going to RREF like a minus 3i, right? And if we do that, we get this matrix, which from that we can see that x1 would equal -1/2 x3, and x2 would equal 0, and x3 is free. So we're basically getting eigenvectors of the form, kind of keep white here. So something in the span of, like if you let like x3 be t, right? Then you've got negative 1/2, 0, 1. Anything in the span of that vector is an eigenvector. And then we do the similar kind of thing. This time we're going to RREF a minus negative 2i, or just a plus 2i. And if you do that, you get this matrix, which from that we can see that like x1 equals negative x3, x2 equals 2x3, and then x3 is free, right? And so for this one, we're getting anything in the span of, what would it be? It'd be negative 1 to 1, right? So anything in the span of that is an eigenvector. So this is an example where you have algebraic multiplicity of 2 for a value, but you're only getting a linear eigenspace for that, right? You're getting stuff along this line. This one, we're only getting a line, which kind of makes sense, right? We're not going to get a plane's worth of eigenstuff for one root, okay? The geometric multiplicity should always be less than or equal to the algebraic multiplicity. But yeah, so that is kind of one of the most important things to kind of take away from this unit, just how by hand we do these eigenvalue, eigenvector problems. And hopefully you see how all this would scale up. If you did, a 4x4, you just have to solve a 4th degree polynomial. And there can absolutely be imaginary roots to these. So, there was a problem in the problem set where we had a rotation matrix, and there's no real vectors that stay in their span, but there are definitely imaginary vectors that stay in their span, right? And the eigenvalues for those would be imaginary as well. So we don't really play around with that too much in a first linear algebra course, but honestly, if you keep going into like applied math and things like that, there's so many places where complex eigenvalues and eigenvectors pop up. And you definitely need to know, you need to think about those kind of geometry things like the rotation in the plane and why they would have complex eigenvalues and eigenvectors. All right, another really important just computation thing from this unit is just diagonalizing a matrix. And so these are problems where I'm fine with you using calculators and whatnot to help you get the eigen stuff that you need to do it. So I'm going to just kind of go through the main points and make sure that you know how we diagonalize like a matrix A like this. So one of the first things we got to do is get all the eigen values and eigenvector stuff that we'll need. So the eigen values of this thing, if you just use a computer or calculator, you should get that lambda, like we'll call it 1 equals 1, and lambda 2, which equals lambda 3, is negative 3. And so we should be getting a matrix D, which equals 1, and then negative 3 with like zeros everywhere else. And so we also need the eigenvectors, so let's do that. So vector, let's say 1, which goes with the eigenvalue of 1, is negative 1, negative 2, 2. And then vector 2, which we can call 1, 1, 0. And vector 3 would be 1, 0, 1. And so these are ones that are linked with the eigenvalue of negative 3. Okay. And so what it means to diagonalize something, right, is we basically need to show the matrix P, which is built out of these eigenvectors, and show that it's invertible, and do out this multiplication so that we hopefully get this diagonal matrix right here. So P should be the matrix built where the columns are just these eigenvectors, so -1, -2, 2 for 1, and then 1, 1, 0, and 1, 0, 1. So, this is, again, a plane's worth of eigenspace for this eigenvalue. And so if you check with like a calculator or something, you'll see that P inverse equals that. And so if we do P inverse AP, okay, we would get, we literally just go and, again, this is all done on a calculator, but do this times this times this. You'll notice, what was it? So you should notice that you get D, okay? Oops. You get D. You get that diagonal matrix 1, 0, 0, 0, -3, 0, 0, 0, -3. And that's what it means to diagonalize something. So it's, it's a very kind of quick computation with the aid of a calculator. Without the aid of a calculator, it definitely takes some time. But this is a matrix that, for a lot of functionality reasons, is similar. Right? I mean, that's by definition to this, but behaves very nearly the same as A. So what we do a lot of times in a lot of linear algebra computations is we'll use this one over A because it's simpler. So that is a very important thing to kind of know from linear algebra, just how we go about doing this, and it kind of acts as like a reduction sort of technique. I always think of it as like, if I was working with the expression x squared plus 2x over x, it's basically the same as x, x plus 2. I can't do math. There's like a whole asymptote at 0, removable discontinuity there, but like it basically looks like a line. And so it's sort of like these things where you could work with this, but you could also work with this way easier thing and just kind of ignore that whole issue. And there's some stuff that's definitely not the same. We've seen that before too, but this is a much nicer thing than A. So work with A if you can. All right, so I think I should do a proof here, just because a big part of linear algebra is also proving things. So this one says, let A and B be invertible n by n matrices, and we're going to prove that AB equals B and BA have the same eigenvalues. All right, so to do this thing, one way we could do this, right, if they're going to have the same eigenvalues, then their characteristic equation would be the same, right? So we basically need to show that the determinant of AB minus lambda I has to equal the determinant of BA minus lambda I. And so you can do this whole problem inside of that determinant part, just kind of cleverly playing around with the matrix multiplication and inverses and things like that. So all you have, too, are that A and B are invertible, right? So we can use A inverse and B inverse to help us, but that's all we got. All right, so I'm actually going to go and just start with this. So determinant of AB minus lambda I, the characteristic polynomial of AB, right? It's true that I could just say that equals determinant of AB, A inverse, minus lambda, A inverse, right? That's just, I'm basically just stuck in, I multiply by 1, right, which I can absolutely do. This is just the identity, and again, I know A inverse is this thing because we're told it's a thing right there in the beginning, right? So then this is the clever kind of trick, I think. We are going to write this as determinant of A times BA minus lambda I, and then A inverse. All right, so what I did there is I basically factored an A out on the left of this thing, right? And I factored an A inverse out on the right. And that would leave I here, right? Because I took A out. I also commuted those, I guess. And then I took A inverse out, so that leaves me I. And then what I'm trying to do is I'm trying to get BA in the problem, right? If I can get BA, That's the thing I want to show. I want to show something about this polynomial, right? So I need to create it in the problem, basically. And then I'm going to use a determinant property. So we know that the determinant of a product is the product of the determinants. So this is equal determinant of A times determinant of BA minus lambda I times determinant of A inverse. And then I'm just going to use another determinant property, okay, specifically for this part. This part at the end, using just determinant properties, we know that's just 1 over the determinant of A. I believe we proved that one, actually, in a previous video somewhere. But if not, I know it was also in, I put up a bunch of these shortcuts with determinant, and I know it was one of those. But then this and this can cancel, okay? And so you have it. So you get determinant of BA minus lambda I equaling determinant of AB minus lambda I. And you could kind of just sum it all up and say something like, since AB and BA have the same characteristic polynomial, they also share the same eigenvalues. Which is kind of a cool little proof. So basically just determinant properties. That's what it kind of boils down to. And this step is clever. To try to figure out how you're going to get that even into the problem is kind of tough. So I guess it's like these two steps together. All right. I just want to do one more example. And it involves that theorem that said, like, if two things are similar, then you get a bunch of these things that are shared by them. Things like their eigenvalues are the same and whatnot. I wanted to show a counterexample to the other direction. So even take the eigenvalues, for example. So you've got a diagonal matrix for both these. And we know that the eigenvalues for A and B then are the same, right? Because the eigenvalues are just the things on the diagonal for a diagonal matrix like that, or upper triangular, I should say. So both lambda 1 for each is like 1, lambda 2 is 2, with multiplicity 2. But I can show you that these two matrices are not similar. So I just want to prove to you basically with, I mean, it's not proof, it's just a counterexample, but show a counterexample, show kind of a technique, I guess, how to take two matrices and show that they're not similar, okay? Basically, it's kind of like a contradiction argument. So I'm going to assume there exists P, okay, such that P inverse AP equals B, all right? So I'm basically assuming the existence of an invertible matrix P. And I'm going to let P equal just arbitrary A, B, C, D, E. Whoops, I jumped the gun there a little bit. D, E, F, G, H, I. Okay? And if P inverse AP equals B, I'm going to let P equal that, and note we should have that AP equals PB, right? That's just, you know, if this works, this is another way to write similarity kind of equation like that. So this is where the cool little thing comes in. So if you do A times P, okay, you're going to get, so if you do AP, you're going to get the following matrix. And then if you do P times B, you're going to get this matrix. And then if you look at what's happening here, so take, let's see, what's one I want to point out. Let's take this and this, right? So we see that like 2D has to equal D, right? And so if you like subtract D over, right, it's basically implying that D equals 0. Likewise, you could see that you could take these two, right, because these are supposed to be equal. So 2g and g equal each other, so then g equals 0. And then you can also get some weird things happening over here, okay? So if you do, let's take that and that, right? So 2f needs to equal 2f plus 7e. So if you subtract the two f's, right, it's basically saying e equals 0, okay? If you go through it, you basically get that a doesn't necessarily need to be 0, but d and g, e, and h all need to be equal to 0. And so then you could create get a little more info for what matrix P would look like. It would look like this. All right, so if we look at what matrix P is here, right, we assume that this thing was invertible, right, because we would need that for it to be similar. And if you look at the determinant of P, right, then you can see, like, if we expand along this column, let's say, right, we would have A times the determinant of 0f, 0i, and then we'd have like we'd have some 0 terms also, but we can just ignore those. But also, this is a really, really important part, this determinant is also 0. And so the determinant of P is equal to 0, but that's a contradiction to the fact that P inverse exists. And so that means that what we assumed is wrong, and so these things can't be similar. But that's like a classic way to kind of show two matrices are not similar. You basically assume they are, and then go through a computation and hopefully arrive at some argument as to why they aren't. Okay, so I think that's kind of a cool problem to see.